Hello everyone and welcome. My name is Carmen Guguta and I'm your host today from Technobis Crystallization Systems. Together with our presenter today, Dr. Hugo Meekes, we are bringing to you the webinar on two robust deracemization methods, Viedma ripening and temperature cycling. First, I would like to share with you a bit of technical information. This webinar is being recorded and will be made available to you tomorrow. You will receive a link with the recording. The same on our website, crystallizationsystems.com. The webinar will be available starting tomorrow. The webinar lasts about 45 minutes. At this moment, you are muted, but you can always send your questions in the chat function of this webinar. If that is not handy to you, you can always write to us at info@crystallizationsystems.com, and also after the webinar, please feel free to write to us at info@crystallizationsystems.com. At the end of the webinar, our presenter will also share with you his email address, so you have quite a few possibilities to get back in contact with us and have your questions answered. For those of you that do not know that well Crystallization Systems, we are a Dutch company located in the north of the Netherlands, leader in three major markets, pharma, agro, and fine chemicals. Our portfolio addresses crystallization, process optimization, and formulation-related research. Shortly, a bit about our products. Are parallel reactors that you can heat and cool in a controlled way. These parallel reactors help you to perform any type of crystallization, salt, co-crystallization, amorphous solid dispersion type of screens, solvent selection screening, solubility screening. When it comes to screening, this is available on all our free products. On these products, the transmissivity technology is also available on all three of them. This technology allows you to determine the solubility curves, metastable zone width, to construct with this information phase diagrams, to perform induction type of measurement. The crystalline, our instrument that works at a slightly higher working volume of about 5 milliliters, comes with a camera technology with the particle view imaging, and it works exactly like a microscope, in situ type microscope, that allows you to see particles as small as 1 micron, and allows you to perform any type of crystallization process optimization. You can check the particle size distribution, habit control, form control, even formulation type of experiments can be performed on this instrument. Last but not least, if you have a Raman spectrometer, this can be connected to your instrument, to the crystalline, and you can follow, as in a normal way you would do with a Raman, chemical reactions, polymorphic transformations. Everything is available on this instrument. This was shortly on our instrument for those that do not know us that well. And now I'm going to our presenter. Our speaker today, as mentioned before, is Dr. Hugo Meekes. He's an assistant professor in the Department of Solid State Chemistry at the Institute for Molecules and Materials at Radboud University Nijmegen in the Netherlands. This is a very short introduction about our speaker, but he will shortly introduce himself and share with you his research topics. And with this, I give the floor to our speaker. Hugo, I'm changing now presenter. Yes. Yes.
Okay, very welcome also from my side to this webinar. I hope that you are all in good health. Today, as Carmen already told you, I'm dwelling on the topic Viedma ripening and temperature cycling two robust deracemization methods. The two images in this slide will become clear during the presentation. First, something about our university. We're located in Nijmegen, which is in the Netherlands, so the northwest of Europe. And within the Netherlands, we're on the east side, close to the border to Germany. And within Nijmegen, we have quite a nice campus, university campus. And the greenish buildings, the four buildings you see here, belong to the Faculty of Natural Sciences, Mathematics and Informatics. Now, around this building, you will find some other buildings which are connected to the faculty. And these are, for instance, the state-of-the-art NMR laboratory, particularly for solid-state NMR. Felix, which is a free electron laser facility providing infrared light tunable with laser intensities. This is the HFML, the High Field Magnet Laboratory, which gives you continuous magnetic fields up to 30 Tesla and higher. And finally, this is the NanoLab, a vibration pore facility where scanning probe microscopy, like scanning tunneling microscopy and atomic force microscopy are performed. So this is quite a nice environment. And within this environment, I am in the solid state chemistry group of the Institute of Molecules and Materials. What we study is the fundamentals of crystal growth. In fact, anything which is related to growth of crystals, we are interested in. So you see here a few topics: crystal morphology, solid-liquid interfaces. That's where the growth happens, of course. Polymorphism, chiral separation will be the topic of today. We studied protein crystals, nanowires, nanocrystals. And at the heart of all these experiments and theories, there's always crystallography. And therefore we have a crystallographer in our group, which is René de Gelder. This is Elias Vlieg, the head of the department. This is me. And this is Willem van Enkervoort, who retired last year, but is still active for a few days per week. Now, the sales pitch of today will be Viedma ripening and temperature cycling, of course, two robust deracemization methods, but also that they give 100% yield in the solids. Of course, this I'll have to explain. And for that, we start by looking at what a chiral molecule is. Of course, you probably know that they come in two fashions, left-handed and right-handed fashion, two enantiomers, and these two are each other's mirror image. Now, a few examples for their effects in terms of bioactivity is the case of limonene, for instance, which is this molecule, which is mirrored to its other enantiomer, to this molecule. Now, the right-handed molecules smell like citrus fruits, oranges, while the left-handed molecule, they smell as turpentine, which is quite a difference. So their bioactivity towards smell is very different. Another example is aspartame. This is a diastereomer, so with two chiral centers, and the LL version tastes 200 times as sweet as cane sugar, while the DD version is rather bitterish. So again, a big difference in bioactivity now for smell. Now, if you go to medicines, things can become worse, because this is the case of thalidomide, which is also a chiral molecule, and the right-handed version was used in the 1960s or thereabout to prevent morning sickness for pregnant women. The downside was that the other enantiomer, the S enantiomer, caused birth defects, and therefore this medicine could not be administered anymore, because it turns out even if you would administer only the right-handed enantiomer, then in the human body there would be a racemization reaction, slowly making a racemic mixture between the two enantiomers, which would be 50-50. So that was dangerous for the unborn child. So therefore, it is important to either separate chiral molecules, or, and that is the alternative, to deracemize them. Now, separation is a classical method, and for that, mostly crystallization is used. Of course, you can use asymmetric synthesis, but to come to 100% pure enantiomers is quite different in most cases. When you use crystallography, you can use diastereomeric resolution, which I will not be talking about, but which is used a lot in practice, but also preferential crystallization, and I'll show you that in some detail. And then there's a nice alternative, which is called coupled batch processes, on which I will dwell very shortly. Now, for deracemization processes, we have three alternatives. One is total spontaneous resolution. This has been known for quite some time. And the two relatively new ones are Viedma ripening and temperature cycling. The difference between separation and deracemization is that for separation, you really separate left-handed and right-handed. And so you have a 50% yield in the enantiomer you want to have. Well, for deracemization, you have a 100% yield because you transform during the process all left-handed and right-handed molecules to one of the two enantiomers. So a 100% yield in the solids. Now, that you can use crystallization for separating chiral molecules was already discovered by Louis Pasteur. That is, he found for a tartrate salt, which was this sodium ammonium tartrate, that the crystals came up into two fashions, and these two were each other's enantiomer. And this made him conclude that the molecules inside the crystals also should have two identities, and therefore we call them now chiral molecules. And he was able to select only one of the two sorts of crystals by simply using a pair of tweezers. Now, a bunch of crystals in which you find these two mirror images, you call a racemic conglomerate. This is a notion which I will use a lot during this webinar. So a racemic conglomerate means I have crystals of both handednesses in a mixture. And that means that in one of the two you have the left-handed molecules, and in the other one you have the right-handed enantiomers. Now this appears, if you look at all chiral molecules, roughly only for 10% of the molecules. They form a racemic conglomerate, so separate left-handed and right-handed crystals. While the majority, some 90%, forms a racemic compound. And that means that within the unit cell of the crystal, you will find both enantiomers present. Then there's a small fraction which forms a solid solution, which is more or less the same as a racemic compound, but then the structure is not so ordered in terms of left-handed and right-handed molecules. Therefore, we call this a solid solution. Now, for separation of left-handed and right-handed molecules using crystallization, we therefore cannot use these two types. We only can work with racemic conglomerates, and that would mean only for 10% of the chiral molecules, but I will show you in time that there are ways to avoid this problem. Now let's look at the classical way of chiral separation, and it is by nucleation and attrition. If you would start from a saturated or supersaturated rather solution of a salt, for instance, and in this case I choose for sodium chlorate, which is in the crystals chiral, that is to say you have a left-handed and right-handed crystals, although in solution the ions are simply achiral. You can compare that they stack in the crystals like spiral stairways, either left-handed or in a right-handed fashion. So sodium chlorate is achiral in solution, but racemic, a racemic conglomerate in the crystals. Now, if you would lower the temperature or wait longer for a supersaturated solution, then after some time you would find the first crystal which would nucleate. And if you at the same time have this magnetic stirring bar stirring the solution, then of course this crystal will also suffer from attrition, and you will make many more new nuclei, which will grow out to new crystals. And they will eat the supersaturation very fast, and therefore you might hope to end only with the enantiomer in the crystals of the first nucleus. But of course the other enantiomer can nucleate during the process, and then you would have again a mixture of left-handed and right-handed crystals. So if this is possible to have sometimes only right-handed crystals, then the question is, what about chiral molecules? Well, this was already suggested much earlier during the 1950s by a Dutch chemist, Egbert Havinga, and he considered the case where in the solution of chiral molecules, where you have a racemic mixture, on crystallization, the conglomerate, and for instance producing only the red crystals, the concentration of the left-handed molecules in the solution would increase relatively to the right-handed. But the racemization reaction in the solution could avoid this scalemic mixture. So the racemization reaction keeps the solution all the time at a 50-50 percentage ratio. And in this way, he said also for chiral molecules, for the same process as I showed you before, I can wait for the first nucleus. If it is a right-handed one, then using this attrition, you end up with a lot of right-handed crystals, and in the solution, the racemization reaction will, of course, maintain the 50-50 ratio. But still, also in this case, the other enantiomer can nucleate, and then you still would not end up with an enantiopure solid. Now this scenery changed drastically with the discovery of this Spanish geologist, Cristobal Viedma, who in 2005 published a paper where he did a completely different experiment. He used again sodium chlorate, but then started with a 50-50 mixture, a slurry of crystals, so blue and red ones, and he added to the solution, besides the stirring bar, also some pearls on glass beads. And by stirring this slurry vividly, so really grinding the crystals down to very small crystallites, he found that after some time he ended up with only one of the two enantiomers in the solid. A very surprising experiment. You see one of his graphs in this publication. One of the two enantiomer crystals disappears in time and the others grow. So let's say the left-handed are converted via the solution to the right-handed crystals. Now, of course, this is still the case of an achiral compound in solution. But still, this was a very surprising thing. And what is very important in this case is that because the solution is always nearly saturated, there's no nucleation. Of course, if you grind the crystals, they become smaller and smaller, and then due to the Gibbs-Thompson effect, the solubility will increase a little bit, but during the process, you will have a very, very small supersaturation, no nucleation. And moreover, you have a 100% yield in the solids again. Because if you have no nucleation, you don't have to be afraid to nucleate the blue crystals, for instance, during this process where everything is transformed to the red crystals. Now, we were a little bit skeptical about this experiment, but then again, it was published, and we were thinking what could be the cause. And we, as Crystal Growth, knew about Oswald ripening, which is a process he has shown for sodium chlorate again. A process where when you have a bunch of crystals in contact with a solution, you don't have to stir or do anything, and you wait, then in the end, only one crystal survives because of this same Gibbs-Thompson effect. It is an effect where the the energy in the surface of the crystal is the lowest as compared to the bulk crystal energy. Now here it is shown for sodium chlorate, where you see two types of crystals under a polarizing microscope. The dark crystals are, let's say, the right-handed ones, and the light crystals are the left-handed ones. And in time, you see that the small ones disappear from the solution, and the big ones start growing. And in the end, you end up with only one single crystal. And of course, this one is either left-handed or right-handed. So Oswald ripening in itself already gives you a deracemization in the solids. The problem is only that it takes quite some time. And especially if you have a few large crystals in the end, then it can take ages before you have a complete conversion to only one single crystal. Now, the mechanism behind Viedma ripening was explained by Makyo Uwaha, and the essence, according to his model, is that you need, besides monomers going from the solution to the crystals, also small clusters, which you make also by the attrition, and they can enantioselectively grow into these crystals. If you want to know more, I refer you to this paper. We wanted to apply this method of Viedma to chiral molecules, so we need a racemization in solution. For instance, this would be for thalidomide, but we also need a racemic conglomerate, and that makes this compound not fit for Viedma ripening. But in the end, we got a good candidate, which was a Schiff-based derivative of phenylglycine. We got this from Bernard Kaptein from DSM, a chemical company in the south of the Netherlands. And this one is readily racemizable in solution by adding some of this base DBU. Wim Noorduin was the one who did these experiments, and you see it's a very simple experiment. You only need a stirring device, a magnetic stirrer in the solution, and you already see this milky solution because you are grinding the crystals towards very small crystallites. And what Wim found was indeed a fast racemization in solution, and in 6 different experiments he found that starting from a small initial enantiomeric excess, which is given by the difference in the 2 enantiomers in the crystals, you get a amplification, a sort of exponential increase of this enantiomeric excess, starting from almost 0 to 100% in 3 experiments to the R side, and in 3 other experiments to the S side. So this was a big success, and I can coin it Viedma ripening 100% yield in the solids. But we went on, and this is René Steendam, another PhD student in our group in those days, and he used a real reaction starting from achiral reactants, these two, towards an enantiopure product, and that is, in this case, the racemic chiral composition of this chiral molecule in a 50-50% ratio. And here the working of the DBU is not so much to racemize this molecule in solution, but rather to catalyze the backward reaction. And because you sometimes go back to these achiral molecules, you also can go forward to form again the chiral molecule. So this is a racemization reaction via the back reaction to the achiral reactants. He used high concentrations, and then you get precipitation. And here you see the result. In time, he starts with only the achiral molecules in the solution. They react, form, because of the high concentration, the blue and the red crystals, and in time, by grinding, like a Viedma ripening, in one pot, you end up into only the S solids. So from achiral reactions in one pot to pure S enantiomers in the solid. He did it for another case, where the isoindolinones with three different types of isoindolinones, and found in the same way in a one-pot reaction a very fast reaction to enantiopurity. Okay, so what did I tell you up to now? We have Viedma ripening, which is a sort of attrition enhanced deracemization. It is limited to racemic conglomerates. You need a racemization reaction in the solution, and it is quite a slow process. On the other hand, you can steer the outcome towards R or S in very ways, which I will not explain, but which you can find in the various references I added at the end of this presentation. And one of them is, for instance, by adding chiral additives, or you starting from an asymmetrical crystal size distribution for the left and right-handed crystals from the beginning. But I would like to see how we can speed up the process. And already in the early days, we published a paper in Angewandte where we looked at what parameters determined the deracemization rate K in this exponential dependence of the enantiomeric excess as a function of time. One of them is the amount of solids. If you have lots of solids, then the process takes longer. That's why you find here this reciprocal B solid, the amount of solids is B. If you increase the racemization rate, the process will also have a higher deracemization rate. Same for solubility. Higher solubility means a higher frequency exchange of monomers between solution and crystals, and again you get a higher rate. And also the attrition, and that's one of the most important ones, for a higher attrition. So if you grind them more intensively, then you get a higher deracemization rate. So let's look at these two cases, amount of solids and attrition. If you increase the attrition by, for instance, adding more and more glass beads to the solution, you see that the rate goes up considerably. You can't go too high with the amount of glass beads because you still have to be able to stir the slurry. But if you then go from this case to an ultrasonic bath with the same amount of beads, and we used a simple cleaning ultrasonic bath for that, then you see you can improve the deracemization rate even more. And what Wim Noordijn did also, he went to Agfa Gevaert in Belgium to use their industrial bead mills, and for a 40 times as large volume scale, he got a very high deracemization rate, as you can see here, because he was able to deracemize this compound he used within 1 hour. Now, there are also limits to that, because if you go too high rates in these mills, in these industrial mills, for instance, at this rate of 3000 RPM, you see in the X-ray powder diffraction pattern of the crystals at the end that you induce amorphous crystals, or amorphous solids, I should say, besides the crystals. And these amorphous solids, they reduce the enantiomer selectivity for building in the chiral molecules or the chiral clusters. And then you get even a reduction in the deracemization rate. So also there are limits. Now the other one which I wanted to show you is that if you go to very low solids, which is on this side of the graph, then you also get an increase in the deracemization rate K. And therefore, Wim used this for the case of this compound, naproxen, which is a medicine. The disadvantage of naproxen is that it is a racemic compound. But on the other hand, if you make the methyl or ethyl ester of this compound, you get a racemic conglomerate. And this is what he did. He made the methyl and could in this way, the methyl ester, and could in this way readily deracemize this compound using sodium methoxide as the racemization catalyst. This took some 4 days, as you can see in this graph. This is, by the way, the logarithm of the enantiomeric excess, giving a more or less straight line. But he went on because if you make the ethyl ester, which is more soluble than the methyl ester, then you get a slow conversion from the crystals of the ethyl ester to those of the methyl ester in solution, and that is depicted here. This is the ethyl ester crystals, and they slowly go to the methyl esters, and that's the one you are effectively deracemizing in this solution. And what you get as a result is this graph where you start from 100% because you don't have methyl ester crystals in the beginning, only a few ones, and they're enantiomer pure because you added those. And then it drops and then goes very fast to 100% in only 15 hours. And this is because you have a gradual feed of ethyl ester molecules via the solution to methyl ester crystals. So via this gradual feed of the compound, you get a faster deracemization, increasing from days to hours. Now, what to do if you have a racemic conglomerate, racemic compound, sorry, and you don't have a racemic conglomerate? Then there are very many ways to circumvent this problem. You can adapt a compound. You can use kinetic racemic conglomerates. So these are metastable racemic conglomerates. You can use salts to produce racemic conglomerates, or perhaps even co-crystals. Now the first one, adapt a compound, you already saw in the case of naproxen, but I want to show you another one, which was studied by Ton Engwerda, who wanted to use Viedma ripening for another molecule than the ones which have carbon as their chiral center. So he came up with sulfoxides, which have sulfur as their chiral center. The problem is they're difficult to racemize, only at very high temperatures, but he found allylic sulfoxides, which are racemizable already at 50 degrees centigrade. They're important molecules because they are part of the chiral pool for synthesis. Now, what he did, he screened a lot of allylic sulfoxides to find a conglomerate, and then in total 24. He could only 14 of these transform to crystals. The other ones either didn't crystallize or it took too long. And of these 14, there was only one which was a conglomerate, and that's this one. So that's 1 out of 14, a little bit close to the 10% which I mentioned earlier. Doing the Viedma ripening on this conglomerate was very well possible, as you can see, and he managed to do that in about 7 days for, let's say, 10 milliliter solution. But he found out by accident that sometimes he produced a racemic compound instead of the racemic conglomerate. So this racemic compound was metastable, but these crystals converted very slowly into the conglomerate, and therefore he had automatically again a gradual feed from the metastable racemic compound to the racemic conglomerate, and that increased the deracemization rate with a factor of 2 to 3. So he ended up with a pure enantiomer in about 3 days using this gradual feed. You can find the details in this paper below. Now you can also use kinetic racemic conglomerates. What I showed you before in the last slide was a kinetic racemic compound. And the case of racemic conglomerates was found by Laura Speaks, another PhD student in those days in our group. She wanted to use Viedma ripening on proteinogenic amino acids. And there are only 3 which are claimed to be conglomerate forming proteins. One of them is 309, but that one is not very attractive because it's a diastereomer, and we had not so much experience with diastereomers in Viedma ripening in those days. Nowadays we have. Asparagine was claimed to be a racemic conglomerate, but turned out to be not. It is a racemic compound. So that's why she worked on glutamic acid, and in fact she needed the anhydrate of it. And if you use salicylaldehyde as the racemization catalyst, and you work in pure acetic acid, sorry, then you can have a racemization reaction between the two enantiomers of glutamic acid. Here is the setup, which is a little bit more difficult than you saw before because you need a cooler because of the high temperatures, and of course now you also need the to control the temperature besides having the stirring bar with the glass pearls in your vessel. But still, for a chemist, this is quite a simple setup, I guess. At 90 degrees, she performed Viedma ripening, and if she started at quite high initial EE, it went quite nicely to 100%. But if she started at lower EE at the start, then you see that in the beginning it went up nicely, but then it more or less saturated in all cases. And what she found was that if she lowered the temperature during the process, then she could get Viedma ripening up to 100% and keep it at that value up to some 70 hours. But you see also already the shape of this deracemization curve is not the typical sigmoidal curve which we're used to. Well, what you found out using powder X-ray diffraction performed on the crystals in the slurry was that in time the conglomerate transforms to a stable racemic compound anhydrate. So this one was not known, but it turns out that also the anhydrate of glutamic acid forms a racemic compound in its stable form. But the conglomerate only transforms relatively slowly, and she could, even by starting at low initial EE, end up in 100% if you stopped the whole process after, let's say, 120 hours. Now, an alternative which she used was to find salts which form a racemic conglomerate, and this is an example of alanine, again a amino acid, and it is the salt alanine parachlorobenzene sulfonate. Already from the space group symmetry, you can see that it is a very probably a racemic conglomerate. And if you look at the alanine molecules, they also have the same handedness. She screened for the salts by looking at 6 different amino acids and 4 different counter ions, all benzene sulfonates. And within these 24 trials, she found 3 pluses, that is to say 3 times a racemic conglomerate. The asterisks which you see are the cases where the compound is, or the salt is claimed to be a conglomerate, but she couldn't find it. In her case, they all formed racemic compounds. Now she used this result on indeed this alanine parachlorobenzene sulfonate, and in a similar setup as I showed you before, and the result is very nice experiment. You see a typical deracemization curve in the form of a sigmoidal up to 100%, and it stays nicely constant at 100%. So perfect deracemization because of this salt, which forms a racemic conglomerate. Now, nowadays you could also consider to use co-crystals. We are still trying to find examples of that. There are 1 or 2 which one of them we found, but I will not show it there somewhere in the reference I give you afterwards. But what I wanted to draw your attention to a paper by Eline Grote on co-crystals in general on multi-component crystals. She made a new classification system of sulfates, co-crystals, salts, and combination thereof, and it's a well-cited publication. Today we have in our group Jan-Joris de Vogelaar, who is working on predicting co-crystal pairs using the Cambridge crystallographic database and using network analysis. Here's an example of predicted co-crystals, which he also found experimentally and which was published in this paper. So we are trying to find more co-crystals which also form racemic conglomerates. Now, another point is racemization in solution. That can be very troublesome. Normally, we go to Floris Rutjes, a professor in our institute, and he knows all about racemizing compounds and reactions. But if it is still not possible, then you could consider using this very nice experiment published by Heine et al. And later on also by Laura Speaks, where you have a slurry which you grind as in Viedma ripening, but the racemization now is induced by pumping the liquid only between the two vessels in both directions. In this way, you have a solution which stays racemic, and in the end, you can end up with only one-handedness crystals in the first flask and the other one in the other flask. So this is not deracemization, but separation, but it works quite nicely even if you do not have a racemization, the racemizing compound. So my conclusion is Viedma ripening is 100% yield in the solids, but in the title I showed you that it also holds for temperature cycling. So a few slides on temperature cycling, which was discovered some 8 years after Viedma's paper by people in the groups of Chiral and Adrian Flood in France and Thailand respectively. You see what they did. They used no grinding, but they only change the temperature of the slurry in time, increasing it, keeping it constant, and then slowly decreasing it again, and repeating this cycle many times. Of course, you can choose the difference in temperature and the cooling slope, which can't be too steep because then you would have might not avoid nucleation of the unwanted enantiomer. But in this way, they found an enantiomeric excess in time, which looks very much like the ones which we found in Viedma ripening. That is this sigmoidal curve. Later on, they also showed that if you want to increase the speed of this deracemization process of temperature cycling, then you can also reduce the temperature difference during the process, and then you can increase again the deracemization time considerably. So you can play with this profile very nicely, and in general, not always, but in general, temperature cycling is fast anyway, a little bit faster than Viedma ripening. Now, temperature cycling is also attractive because you can, the experiment is relatively simple. You could even use a crystal 16 or a crystalline for that. And here I show you some results from the group of Marco Mazzotti, where they used the compound of Wim Noorduin to study the effect of different cooling rates in this temperature cycling experiment. And what they found was that if the rate is small, of course, also it takes a longer time to do the deracemization. If the rate is higher, then you can increase the decrease the deracemization rate. But you also can see that going to a steeper and steeper curve doesn't help you much more in the end. So green is slow, yellow, blue, and red are more or less comparable in deracemization time. Now, of course, everything I told you about Viedma ripening, besides that you don't grind anymore in the case of temperature cycling, you can use also for temperature cycling. So you can avoid the problem of racemic compounds by adapting the compound and all the other options. So now I can conclude both Viedma ripening and temperature cycling are 100% yield, give 100% yield in the solids and are two robust methods. Now in conclusion, we find two robust deracemization methods. They need racemization in the solution, and for racemic compounds you have various alternative routes. It works also in a one-step synthesis from achiral components for a reversible reaction combined with precipitation for a conglomerate forming compound. And then I summed up all the ways in which you can increase the rate of the deracemization, and with that decrease the deracemization time. But what I also showed you, that you should not be fooled by a supposed racemic conglomerate or a supposed racemic compound, because you need to know the phase diagram, especially the solids which are formed in equilibrium as well as kinetically, quite well to avoid problems during these processes. But that also holds for classical separation methods. I want to thank these 4 people and of course the funding agencies, a lot of people which were involved in all the experiments. And finally, here you have a list of papers we published during the years. I added the titles so you can pick them out easily, those which are of interest to you. And as Carmen already mentioned, that in case you have further questions, please feel free to send me an email. I will be glad to answer if I can. And with that, I would like to give the floor back to Carmen.
Thank you, Hugo. We have just leave your slide up, Hugo. Yes, okay. Please. We have a few questions. The first question is, if you have a small amount of new compound, but you are not sure if it is a racemic compound or a conglomerate, what would be the first choice to determine which it is?
Wow, that's a good question, because we normally would always use X-ray diffraction. And if you don't have any amount of one of the pure enantiomers, but let's start with the case that you have a little bit of the pure enantiomer also, then you could do a powder X-ray diffraction experiment. So in the diagrams, you will expect the same patterns for a racemic conglomerate as for the pure enantiomer. Now, if you do not have that, then life becomes hard, I would expect. You might hope that the compound already it has some known properties which you can use to select a method for HPLC, high precision liquid chromatography, Chiral HPLC in particular, and hope to find 2 retention times for the 2 enantiomers, and then separate them in that way. To have a little bit of one of the 2 enantiomers, but I don't think I know any other method.
Okay, thank you. I hope, Adrian, this answer answers your questions. I take another question now. The fact of, that a conglomerate slurry can convert into an enantiopure slurry could imply the conglomerate is not a thermodynamic state, but rather a kinetic?
Yes, that's a very good point. And for that, I would like to go back to one of my slides, which was this one, where you see, in fact, exactly what is the matter. If you have a slurry like this, even if you don't move it at all, you don't change temperature, then this is not the thermodynamic stable state. And that is because of the high energy which is in the interface between crystal and solution. So the thermodynamic most stable state is one which is on the right hand side, where you have a saturated solution in equilibrium with one crystal with a shape which also is dependent on the energies, interfacial energies of the different facets on this crystal. So also the shape has one particular shape, which is the equilibrium shape in contact with this saturated solution. So this is the equilibrium situation, and this is indeed metastable. But once more, going from the metastable phase solution, slurry, to this case, takes a very, very, very long time if you don't do anything else than simply wait, and that is what you do when applying Oswald ripening.
Okay, thank you. Another question. Many thanks for the nice presentation. Do you think thermocycling will be easy to scale up?
Well, I'm not so very familiar with industrial crystallization problems, but my idea in the beginning of this research years ago was that Viedma ripening was much more easier, because I thought there's a lot of energy involved in constantly increasing the temperature of a large reactor and again decreasing it and cycling it in this way. And I thought there would be not so much energy involved in grinding the slurry. But later on, I learned from, well, probably engineers or chemical engineers that this might be the reverse. I never studied it in detail, but this is an interesting question, in particular because, as I showed you, for temperature cycling, you can also, in time, reduce the temperature difference of the cycles, and with that, first of all, gain a higher rate of deracemization, a smaller deracemization time, and secondly, of course, that will cost you less energy.
On the same line, another.
On the same volume, yeah.
No, what I mean is another person is asking, has anyone performed Viedma ripening at an industrial scale? If you know about this.
Yeah, the latter part of your question is very important. People don't tell us everything because, of course, it's a very attractive method also for people in industry. And once they have found a way to use it, I guess they don't tell easily everybody that they're doing this. I know people have tried it on a larger scale than we do, and that is very well possible. No problem at all. But whether it's really used for production, I have no idea.
Okay. Another question. From a thermodynamic point of view, which of these systems, enantiomer, conglomerate, racemic, is more stable?
That depends very much on the compound. In principle, only on the compound and not on the solution, or the solvents, I should say. As long as you don't have chiral solvents, then in any solvent, this is a little bit tricky what I'm saying, but in principle, you could say that independent of the solvent, only the compound determines whether it wants to be a racemic compound or a racemic conglomerate. Of course, there can be a temperature dependence. So if you would look at the phase diagram, temperature versus phases, then you can in many cases can find transitions from, for instance, a conglomerate to a racemic compound. We also have found these transitions in atropizomers, that these are molecules which have an axial chiral symmetry, which we also were able to deracemize. And there we used, in fact, this transition from the racemic conglomerate to the racemic compound. But in principle, the compound determines whether it's a racemic compound or a conglomerate, and whether it is temperature dependent in that choice.
Okay. Another question, has there been much or any work on predicting stable racemic conglomerates?
Well, that is a thing which we have nowadays, we would say, on our bucket list. Sorry. We have done quite some work on polymorph prediction in the past. Now, officially, a racemic conglomerate and a compound are not different polymorphs, but of course, the situation is comparable to the case of polymorphic forms. And in principle, you could use crystal structure prediction to find out which of the two is the most stable, the conglomerate or the compound. But on the other hand, crystal structure prediction is for most of us still in its infancy, because you need very, very strong computational forces, for instance, which are provided by Marcus Neumann in his company, to have reasonably reliable predictions. So I think we are still far from that. What we're trying to do now is, for the case of the co-crystals, for instance, to see whether we can find families of molecules. So a family would mean molecules which differ mutually, but in not too many groups. And that whether in such families racemic compounds would be more favorable than racemic conglomerates, or the other way around. And if you could find different families with a preference for either forming racemic compounds or racemic conglomerates, then I think you have a first step towards this prediction. But this is still far to go.
Another question. I must say there are many questions coming in. We will take one or two more and then we finish, because we are. I promised it will be 45 minutes and it's already longer. But it's good to see this interest from people. Many thanks, and people. Great presentation are mentioning what are the effects that lead to racemization of one enantiomer into another in our body? How can we test it before introducing it into the body?
Wow. Now I didn't mention this, but from education, I'm a physicist, and I'm working in a solid-state chemistry group, and therefore I learned a little bit about chemistry during the years. But especially if you go to biochemistry, because this is rather a biochemistry question, I would say. Yeah. I'm really well, I'm ignorant. So for that, I would like to refer you to synthetic chemists or biochemists.
One more question. Just a second. If no nucleation is observed, then what could be the strategy to precipitate required diastereomer?
A diastereomer?
Yeah.
Well, nucleation or no nucleation is of course independent. Well, is independent of whether you have a diastereomer or a normal conglomerate or a racemic compound or whatever. In that sense, nucleation is a theoretical, or sorry, experimental and theoretical problem in itself. Also needs a lot of study still. But if you don't get crystals, our tricks are the standard tricks chemists use, namely adding some dust or scratching the glassware or cooling it shockwise, put it in the freeze, which is for the crystal grower not a very nice thing to do, but okay, sometimes we do it to get crystals. And be patient. What we often find is if you put a vessel with a solution which you have been looking at for days or perhaps weeks on the shelf, and 1 month later you come back, then it turns out that suddenly crystals have appeared. Of course, patience is in many environments difficult, but this is a good way to proceed, I would say. Now, as I said, we are interested in crystal growth, but we're not really crystal growers. So we study the growth and also nucleation, but not, especially the latter, not in such detail yet. to give really practical advices in that. I'm sorry.
Yes. The last question from Laura Hernandez. Thank you for the very nice presentation. Any idea to try to crystallize a pure enantiomer that is amorphous? We have crystallized the racemic compound, but it is very difficult to achieve the crystalline pure enantiomer. Any tips for her?
Yeah, well, the question there is again, and of course you do not know that, but the question is again, what is the phase diagram? Is the racemic conglomerate in terms of energy far away from the racemic compound, and perhaps also far away even from the amorphous material? That is very well possible, and in that case, energetics already make the nucleation of the conglomerate very unfavorable. Of course, kinetics, so the ways you want to get the crystals, like applying a high supersaturation or shock cooling or whatever, can sometimes help to get this metastable phase. But if you always get the racemic compound and never, or the amorphous solid, then the chance that the racemic conglomerate is near to the racemic compound in energy, I would say is not so very high. So I would not know of any tricks unless you would have found in another way the enantiomer pure material, and then of course you can grow crystals from the enantiomer pure material, but perhaps you meant that this gives this amorphous compound already. That is not clear from the question. And what I wanted to say, once you would have gotten these enantiomer pure crystals from an enantiomer pure solution, then of course you could use them as seeds in a racemic solution and hopefully grow them further.
Okay, thank you, Hugo. There are many questions coming in, the same as messages of thanking you for this excellent presentation. I will share everything with you immediately after this webinar, and all the questions will be addressed in the coming days. Some people are also asking for the slides of the presentation. We will be in contact with you either by the end of today or tomorrow, definitely, with all of you sharing all the information that we have available. Hugo, once again, thank you very much for bringing this webinar closer to us, sharing all your knowledge and experience with us. And hope to hear you again here with another topic.
Okay, it was my pleasure.
Thank you.